All right, we've seen Black-Scholes. Now let's see a generalization. So generalize Black-Scholes. All right, so how do you generalize the Black-Scholes equation? So one cool example in chapter 8 is considering what if borrowing isn't free. So remember, in the Black-Scholes equation, we assumed you could go short a stock and there was no cost to doing that. You can short as much as you want. There's no interest rate you have to pay or anything. But that's not true. In the real world, if you borrow someone's stock, you have to pay for the privilege. So how does that work? So let's start doing our derivation. So let's assume we have a log normal asset. So that's the mu s dt plus sigma s dx. So log normal. And now we have our position pi. It's going to be long the option, short the stock. And then, so this is just like in Black-Scholes. Now the equation that describes the change of our position is going to be dv minus delta ds, except this time there's going to be more. We're going to have to pay interest here. So there's going to be a minus r. R is going to be our interest rate we pay as we borrow stock. And then it's going to be the max of 0 delta s dt. All right, what are these terms? So R is our interest rate for borrowing. The max of 0 delta, this is how much we're going to borrow, and the price. And then dt is just time step. So this is the interest rate times the number of shares times the price times the time step will give the total amount of interest we pay in one time step. And that'll be the change of our position. Will be the option changing, the short position changing, and we're paying interest. So why is it the max here? So the max part, if you think about delta is the number of shares that we've gone short. So if delta is greater than 0, then we are in fact short. If delta is less than 0, we're actually not short. We're long the stock. And so the max here, if delta is positive, it'll just be delta. And if delta is negative, this max will be 0, in which case this is indicating we're not paying any interest if we're long the stock. We're only paying interest if we're actually short the stock in the time step. All right, so now let's keep going. Let's just do the other steps of deriving Black-Scholes from here. And so what we want to do is expand dv using Ito's lemma. And so if you remember, this was partial v with respect to t dt plus partial v with respect to s ds. And you have to have the squared term. So sigma squared, s squared, second derivative of v with respect to s dt. And now get the rest of the equation, minus delta ds minus r max 0 delta s dt. Running out of room. Okay, now let's group up terms. We have a t, a t, and the s, ds. So when we group the s's together, we get partial of v with respect to s minus delta. And then if we want to set this to 0, so we want the randomness to go away, we can choose delta. So if we set this to 0, that means that delta equals partial of v with respect to s. And so we do that choice, and these go away. And we're left with the dt's. So d pi equals partial v respect to t plus half sigma squared s squared second respect to s minus r max 0 delta s. And that whole thing dt. All right. So this is looking familiar. We just have this new term. And so the next thing we think is that there is no randomness. There's only dt, the deterministic. And so by the no arbitrage argument, this will be the risk-free rate proportional to the size of our position times dt. So this is just risk-free interest. And then set these equal. And we get, let's write out all the terms here. So I'm setting these equal. Let's also expand out pi here. So this will be r v minus delta, which is partial of v with respect to s dt. So I'm going to set these equal and divide both sides by dt. We get partial of v with respect to t plus half sigma squared s squared max of 0 and delta times s, and then that equals rv minus r partial v with respect to s times s. So this is v minus delta s. All right, and now just collect all the terms on the left. Partial v with respect to t plus a half sigma squared s squared. Second derivative with respect to s plus rs partial v with respect to s minus rv minus r max 0 delta times s equals 0. Here it is. Is that right? That looks right. So this is the Black-Scholes that has been generalized so that it has borrowing. And one of the interesting things is that this term here is nonlinear. Nonlinear. So what does that mean? That means that this is a stochastic differential equation that is nonlinear. So when I start hearing that, I think, how am I going to solve this analytically? But then I think, I don't have to. I can just do it numerically. Who needs to solve it analytically? So this is pretty cool. This is our first example of generalizing the Black-Scholes equation. And our assumption was borrowing stock isn't free. It takes an interest rate. We added a term to our change of our position and just went through the same Black-Scholes derivation, and we come up with our stochastic differential equation at the end, and it just has a new term here, and it's cool because it's nonlinear. Neat stuff.